So I think we only have, okay, let's look at the calendar. It felt like there's a lot of the semester left, but actually it's not. So if you look at our calendar, so today is the 19th. Okay, so today's the 19th, and then we have the 21st, and then we have the 24th. So really only have 3 days total for the end of for the rest of the semester. So I was thinking, oh, well, let me see if I can finish up the next 2 chapters, but really, we don't really have that much time. So we're gonna have to sort of rein in what I thought I'd be able to cover. I was trying to cover enough so that you would have all of the information that anybody who's successfully gone through organic chemistry would be able to do. And we were running a little bit behind schedule because usually if you go slower, people usually do better. And I went a little bit, I think a little bit too slow. So I just would still like to cover a couple of things before the end of the semester. Let's see if I can get that taken care of. Okay, so this, I believe, is the last homework that we covered before we stopped last class period. And there's some things, cyanohydrous in nature. I'm never going to put that on a test, but it's kind of interesting. And then we're up to the Wittig reaction. I think this is where this I believe is the last slide that I actually had at the end of last class period. So what do you do in the Wittig reaction? So what I'm going to say is don't worry so much about the reaction mechanism of the Wittig. All I'm going to say is there are a couple of reactions in the remaining part of this chapter on ketones and aldehydes. So all I'm going to say is what you want to do is for the Wittig and for the imine and the enamine reaction, just know the product. I wouldn't worry about the reaction mechanism. The reaction mechanism, if I had to do the reaction mechanism, it'll be like a good bunch of steps. And so I think we'll just not worry about the reaction mechanism. But it's basically a nucleophilic addition reaction mechanism, but it actually involves the oxygen of the carbonyl dropping off, and then your not the nucleophile that was originally there dropping off, but the oxygen of the carbonyl dropping off. But we won't worry about the mechanism. So all we're going to say is for the Wittig reaction, all you do essentially is you convert a carbonyl oxygen into a carbon. So you convert a ketone or aldehyde into an alkene. So that's the overall effect of the Wittig. The question, of course, is what exactly gets attached where? So to do this, you actually have a Wittig reagent. So what's our Wittig reagent? It has triphenylphosphine. It's a ylid. So it's got a positive charge on the phosphorus and it's got a negative charge. It's a carbanion on the carbon that eventually becomes this carbon. And then it has whatever R groups you happen to have on the original alkyl halide that you start your reaction with. And then you end up with an alkene. So looking at this, so let's look at what actually goes on here. So you got an aldehyde here. You got your ylid. So this ylid has 2 hydrogens on the carbon. So this carbon replaces the oxygen. So then you get this carbon right here. And then what's attached to it, because it's in the condensed structure form, there are hydrogens there, but you don't actually draw in the hydrogens. In this case, you've got this ketone. Here's our ylid. It's got 1 methyl group hanging off of the carbon that eventually becomes the double bond carbon. So you replace that oxygen with this carbon. The triphenylphosphine drops off. We're not going to really worry about the structure of the triphenylphosphine. It comes off, it gets the oxygen that used to be on the ketone or aldehyde, but we don't really need to know that because usually that's just junk that you throw away out of your reaction. But your carbanion is on the ylid. So that carbon attaches here, and whatever is attached to that, there's 1 methyl group. So you end up with one methyl group and the original ketone and the original aldehyde is still there. So you just have to recognize what is the what are the things that you have attached to the carbon that's coming in. And I would not really worry about the mechanism at all. But you should know how to get the Wittig reagent. So how do you get the Wittig reagent? So this is the Wittig reagent. You got a positive charge on the phosphorus, a negative charge on the carbanion. And you can you can abbreviate the phenols as pH groups. And how do you get that? Well, you also can write this as a resonance structure that has a double bond between the carbanion carbon and the phosphorus. But how do you get to that Wittig reagent? You take triphenylphosphine, react it with a primary alkyl halide. The primary alkyl halide kicks out the X, and this carbon of the primary alkyl halide attaches to the triphenylphosphine phosphorus, and then you get this. And then you have, at this point, it's not a ylid. It's a neutral compound. And then you take a base, pull a hydrogen off, and then you get the ylid, where the phosphorus has a positive charge and the carbon has a negative charge. And this CHR, this is what ends up attached to the, in place of the oxygen. So this carbon is what goes in place of the oxygen of a ketone or aldehyde. And because this is, it goes by an SN2 reaction mechanism, you really do need to have a primary alkyl halide as opposed to a secondary alkyl halide or tertiary alkyl halide or other stuff. Okay, so let's look at, so here's the mechanism that you're not responsible for. And let's actually look at the product in the form of Homer problem. So this is a nice, simple, Wittig reaction. Not going to worry about the mechanism. So that first reaction is the actual Wittig reaction. The second reaction is making the Wittig reaction. Here. Okay, so let's look at the first reaction, which is the Wittig. And of course, you know, I did not spend too much time on actually freeing up the reaction. So it's missing the lines that I would normally draw in, and I did not do the subscripts for the numbers in your reaction. Okay, so what happens here? And this is a regular single bond. I just drew it with dashes because it's easier to draw it with dashes. Okay, so our first reaction is the Wittig reaction proper. And our second reaction is the generation of the Wittig reagent. Okay, so let's see what happens here. So what happens here is this part replaces the oxygen. So the oxygen drops off and you replace it with the carbanion. So if I draw it like this, here's my ketone. This is where the oxygen would be, but I'm replacing it with the carbanion. So in this case, I would end up with this product. So easy enough to see the product. You know, if you try to do the reaction mechanism, it involves so many steps that, you know, it can easily get a little bit too much memorization. And it's not immediately obvious, you know, exactly how the reaction mechanism goes. So I'm just going to say, don't bother. All right, so what about the generation of the ylid? So this is a primary alkyl halide. So our phosphine is going to go in here and it's going to kick out the chloride. So then you're going to get your triphenylphosphine attached to that carbon, with that hydrogen here, and that methyl group hanging off of here. Now you realize this Wittig reagent actually had 2 R groups, and I could have 2 R groups too. It's just not as favorable a reaction to generate the Wittig reagent. All right, so this is not the ylid. For it to be a ylid, you need to have a negative charge on the carbon and a positive charge on the phosphorus. So this is not the ylid. So then you take a base, and this is where our base comes in. Your base comes in, pulls off a hydrogen, and then that the pair of electrons that's between the carbon and that hydrogen goes back to the carbon, and then you end up with and this is the ylid. So then this will react with an enol ketone or aldehyde to give you the alkene. Okay, so that's all we're going to do with the Wittig. We're not going to do anything else with the reaction mechanism. We're not going to look at the natural product, where it's found, and so on. So there's all it is that we're responsible for the Wittig. Just do the reaction. Okay, so then let's look at, oh, yeah. I do have the homework today. I did post it. This is probably not the last homework. I do have a couple more homework. The next chapter, we're not going to do any more homework because we're running kind of behind schedule, but I have a bunch of homework for this chapter. All right, so next. So this is the formation of imine and the formation of enamine. So basically, these are all addition of nucleophile doing nucleophilic addition onto a ketone or aldehyde. So if you add an amine, there's a whole reaction mechanism involved where this oxygen of the ketone drops off, because this actually turns into water and it drops off. And then the nitrogen forms a double bond and you end up with the imine. But we're not going to worry about the mechanism. All we're going to say is you get a primary amine, react with an aldehyde or ketone, you will get an imine. Here's the structure of the imine. Primary amine, that's what happens. So what's a primary amine, you ask? Okay, so it's sort of like primary alcohol, secondary alcohol, tertiary alcohol, that's the same sort of thing. So here's an amine. Ammonia would be NH3, but this is an amine because it's got 1 R group on there. This is a primary amine. Why is it primary? It's got 1 R group. This is a secondary amine. Why is it secondary? It's got 2 R groups. This is a tertiary amine. It's got 3 R groups. So the number of the amine just goes by the count of the number of R groups you have on your amine. Okay, if you have a primary amine, you'll get an imine for the product. Secondary amine, you'll get an enamine for your product, and tertiary amines don't usually do reactions like this. So this is addition to an aldehyde or ketone, and all I'm going to ask you to do is just know the product. But it actually involves nucleophilic addition followed by the removal of the carbonyl oxygen as water, and then you form a double bond for a primary amine. So this is a primary amine. So, but do note that this bond, that they're drawing it like an angle, and the reason why they're drawing it like an angle is because the amine it actually is sp2 hybridized. So it's got the lone pair occupying one site, the double bond occupying one site, like in a VSEPRT structure, and the alkyl group of the primary amine occupying one site. So it actually is bent like that. Okay, so what you do is you take a ketone, add a primary amine. Well, how's it primary? You got NH2 and you got 1 R group, primary amine. And then you end up with that nitrogen attached in place of the carbonyl oxygen and that R group hanging off of it like that. That's all it is. And that's all I'm going to ask you to do. No mechanism. The mechanism is pretty involved. So you'd have to do a, well, you can write it on your piece of paper, but it's if you had to memorize it, it's like a, like a 10-step mechanism. So we will not do the mechanism. And we're short on time as it is. Okay, so there is my imine preparation. Here's the mechanism. So you see what happens. This is basically a nucleophile that adds on nucleophilic addition onto a ketone. You get this, you get the better leaving group by adding on a hydrogen onto the OH minus, and then that drops off, and then this forms a double bond, and then you get the imine. But never mind the mechanism, not responsible for mechanism. You just have to know the product. Okay, so some imines in nature, it's interesting, but we're not going to really worry about that too much. Okay, so then if you have a secondary amine and you react it with an aldehyde or ketone, what do you get? You get an enamine. So what's an enamine? It's an amine that has a double bond right next to it. So there's my ene, and here's the amine. And we're starting out with a secondary amine. Because we're starting out with a secondary amine, the hydrogen can't drop off, allowing you to have a double bond between the nitrogen and the carbonyl carbon. So then you form a double bond here. Okay, so here's a ketone. Here's a secondary amine. How is it secondary? You got a nitrogen with 2 R groups attached to it and 1 hydrogen. So that nitrogen attaches in place of the oxygen. There you go. And then the 2 R groups that are on the amine show up attached to the amine, nitrogen. And then next to the carbonyl carbon, you form a double bond. You form a double bond in a convenient spot, preferably one that's stable. But you can, it's kind of a minor point, which is, Zaitsev's rule and so on. So you know which one would be the more stable one, but you don't really, I would not count off if you give me the wrong regioisomer. Okay, so that's my enamine. So here's the mechanism, not responsible for mechanism. So it actually does a nucleophilic addition, just like our primary amine. And then the OH drops off as a water molecule. You form a double bond, and then you got a positive charge on the amine nitrogen. You don't like having a positive charge on the amine nitrogen, you move a pair of electrons over there, and then you have to have a double bond on the carbonyl carbon on either one side or the other. Okay, so there's the mechanism, not responsible for mechanism. So secondary amine, you get an enamine. That's all we're gonna know. Okay, so here's our ketone. You add a primary amine, you get an imine, where you get a double bond between the carbonyl carbon and the nitrogen. There's my imine. No charges anywhere in the molecule after it finally forms the amine. The enamine you get with a secondary amine. You end up with the carbonyl carbon having a double bond on the carbon next to it and not to the nitrogen. And the R groups are still attached to the amine. Secondary amine, enamine product. Okay, and what's kind of nice about this is sort of a reversible reaction. So if you add water, you will regenerate the ketone or aldehyde. But that's kind of a minor reaction that we don't really, I will not ask you about. But here's the imine and enamine reaction. So that first amine is a primary amine. That second amine is a secondary amine. So it says primary amine goes to imine, secondary amine goes to imine.
Oh, you're good.
Everybody got one? Okay. All right, so let's take a look at this reaction. Here's our amine reaction. Okay, once again, we're not going to worry about the mechanism. They both do involve nucleophilic substitution followed by the removal of water and then moving some hydrogens around to end up with the final product that doesn't have any kind of charge anywhere. Okay, so here's my aldehyde, and you can do the reaction with either aldehyde or ketone. Usually aldehyde reactions are usually easier for everything. Okay, so here is, what kind of an amine is this? How many R groups does that thing have? It's got one, so it's a primary amine. What kind of an amine is this? This is a secondary amine. So what are we going to do? We're going to replace that oxygen with the nitrogen. So that is going to go there. This is going to go there. Okay, and then you're going to end up with enamine. Sorry, imine. So here's my imine. Okay, so that nitrogen replaces that oxygen there. Okay, that amine has two alkyl groups attached to it. And then we're going to form a double bond at the carbonyl carbon. So there you are. Oh, okay. Okay, so imine, enamine. So all you're doing in both cases is you're replacing the carbonyl oxygen with a nitrogen. And then if you have a primary amine for your reactant, you end up with the double bond between the carbonyl carbon and the nitrogen, like the original carbonyl. And but if you have a secondary, then you end up with a double bond on the carbonyl carbon to the immediate carbon next to it. So there you are, imine and enamine products only. So what you would do is you would need to write down like a generalized equation for your equation sheet. Okay, so we're almost done with all the reactions in this chapter. Let's see, except for a reaction that you that's actually useful in a way because you use it for doing a protection of a ketone if you're trying to do a reaction somewhere else other than the ketone that you're trying to do that you're trying to protect. This also is addition of water onto a carbonyl carbon. So what you do is you add water to it and then you end up with a gem diol. So if you have a formaldehyde, you add water to it, you end up with the OHs and the original hydrogens still there. You add the water onto here, you end up with the original oxygen turning into an OH, and then the additional coming in water giving you the OH. So you get that. Okay, now this is kind of interesting. So if you have a very unhindered carbonyl carbon, you will get primarily the addition of water in its natural state. So if you have formaldehyde, you have the hydrated version of formaldehyde in 99.9% under normal conditions. If you have acetone, and acetone is not a whole lot more hindered than a formaldehyde molecule. It is a little bit more, but in that case, you only have 0.2% of the gem diol. You mostly have just the ketone. You don't get very much of the diol. And of course, if you got something in between in size, then you get like 60% if you've got an acetaldehyde where you just have one hydrogen on one side. Okay, so what are we doing here? So I could ask you for the reaction mechanism for this because this is just a classic nucleophilic addition using the nucleophile OH minus. That's all it is. And you don't even remove any waters or anything. It just stays all there. So my nucleophile comes in, OH minus comes in, kicks out a pair of electrons. You end up with a hydrogen attached to the classic nucleophilic addition reaction mechanism. And you end up with a carbonyl carbon that has two OHs attached to it. Okay, so that's just plain old nucleophilic addition. I could ask you that mechanism because all you're doing is you're just adding a nucleophilic addition. Okay, I'm not going to ask you for the acid catalyzed just because you have to move some hydrogens around, and I did not go over a lot of things that have not responsible. I didn't go over a lot of reaction mechanisms where you had to move the hydrogens around in the correct way. So I'm not going to hold you responsible for that because, you know, I haven't gone over a lot of it. It would be kind of unfair for me to, at the last minute, ask you to know that. So I'm not going to. Okay, so we'll skip the acid catalyzed. We'll go with the base catalyzed addition of water. Now, the other thing you can do is you can actually add alcohol to the carbonyl carbon instead of adding water to the carbonyl carbon. So if you add alcohol, if you add two equivalents of alcohol, the first equivalent will go in and then you will remove the OH from the carbonyl, the oxygen will drop off, and then you can add on another alcohol molecule onto there, and then you end up with an acetal. Now, your book does not distinguish between acetal and ketal, but ketal is what you get if you have a ketone. If these are both R groups, it's known as a ketal. If one of these is a hydrogen, then it's known as an acetal. But in any case, you're adding on alcohols. If you add one equivalent of alcohol, you'll get a hemi, like a half, you know, hemi like hemisphere. You'll end up with one OR group and the OH still there. If you add on two equivalents, then you'll end up with the acetal or ketal. Let's see. Oh, goodness. It says looking for TV. Must be a wireless problem. Is my battery running low? No, it's still at 60%. Oh, let's see. I think it should come in pretty soon. A little bit of a delay. AirPlay, looking for TV. Let me see if it's because I just don't have enough energy. Laptop because I need to. I didn't bring my Stop airplane. Okay, we're back. Okay, so you can add on 2 moles of alcohol, or you can add on 1 mole of alcohol, and then if you add on 1, then it would be a hemi-acetal or hemiketal. Okay, so this is the way that organic chemists do reactions. If you've got a ketone, which is kind of sensitive and prone to reacting, if you got something else there and you got a ketone, and you're trying to do a reaction on some other part of the molecule, the way you would do it is you would do a protection group thing, and you would use a diol that actually has an alcohol on both sides of the same molecule, like ethylene glycol. And then you would replace the carbonyl oxygen with the diol. So this is a acetal, but it's a cyclic acetal, and it's kind of stable. It's stable unless you add an acidic water to it, and then it'll just collapse back to the ketone. So the advantage is you can then have the diol, the cyclic acetal, to protect your carbonyl carbon so that it doesn't do any reactions. And then you can remove this and have it go back to the ketone by adding acidic water to it. So this is a well-known synthetic method for protecting your carbonyl carbon. And this is how you would do it, because it actually is a totally reversible reaction. The reaction will go forward if you are able to remove water. So you use this special piece of equipment to remove water. So here is our acetal formation with our 2 alcohols. And you could actually look at the reaction. I'm not going to hold you responsible for the reaction mechanism. The reaction mechanism for forming the hemiacetal is pretty straightforward. The reaction mechanism for forming the acetal is not, because then the OH has to drop off and you have to add on another OR. So this is just a classical addition of a nucleophile onto a ketone or aldehyde. You end up with that. It's acid catalyzed, so you see the little bit of hydrogen moving around that you did before you get to the addition of the alcohol onto the carbonyl carbon. And then after you get the addition of 1 alcohol, then you do another addition of the alcohol. So then this drops off as water, and then you end up with a carbocation, and then your second alcohol comes in, or you could do it in 1 step. Your second alcohol comes in, and then you end up with the acetal, where you've added on 2 alcohol molecules onto the carbonyl carbon. But I don't think I will hold you responsible for that mechanism. I'll just hold you responsible for plain old nucleophilic addition, not for addition of 2 molecules of water, because then you have to look at the thing and remove the OH off of the carbonyl carbon. Once you generate the acetal, it is a reversible reaction. You add water, a little bit of acid, it goes back to the ketone. You got your diol protected, the cyclic cyclic acetal formation like this. You add acidic water, it drops off, you get back the ketone. So this is the protection group that you can use to protect the ketone, as in, like for instance, if you're trying to do this reaction. So you got an ester over here, you got a ketone over here. Ketones are more reactive than esters if you're trying to do a reduction on it. But you can protect this group and then do the, so if you do the reaction just as it stands, it'll react here and not react here. So if this is what you are trying to get to, you're trying to do the reduction on the ester but not on the ketone, you can't do it normally. So then you have to protect this group. So how would you protect that group? You would protect that group by using the protection step, where you've got a diol you turn the ketone into an acetal. You do the reduction on the ester, and then you add water to it and go back to the ketone. So you deprotected the ketone. So that's the protection, deprotection process. I don't think I would, there's not going to be a synthesis problem on the next test where I ask you to do this, but you've seen it. If somebody mentions something about protection group, you'll know what they're talking about. You can also form cyclic acetals and cyclic hemiacetals. And where would that show up? It shows up in, let me go back to it shows up in carbohydrates. So all your sugars are cyclized alcohol attached to an aldehyde or ketone, and you get a cyclic acetal or hemiacetal. So this is a hemiacetal you can add on. And the way you attach one sugar onto another sugar is to do that second addition of alcohol onto one of the OHs on the next molecule. And then you can link a whole bunch of these in a long polymer of glucose molecules or long polymer of lactose molecules or something like that. So that's how you would use it. But let's go back to this slide. So this is a summary of all the reactions that we covered in this chapter. So, and this, all I did is I just covered up the thing and I changed the original molecule. The original molecule is a cyclohexane, but I changed it to simple acetone. So, if you think about all the number of reactions that we've had this semester, we've had a lot. Obviously, I can't put all the reactions that we covered this semester on the test, but then your test would consist of nothing but reactions. And I try to not do that. So that means, and we have the other reactions, we've already done a couple of other, oh, I forgot to send the sign-in sheet around. Okay, so the sign-in sheet around, coming around. So all it has on there that's useful is that we have the date of the final exam, and don't forget there is a final, cumulative final for this class. Okay, so what I would do for the reactions at the final, so there's we're not getting any more exams, we're not getting any more quizzes. The only thing we're gonna get is we're gonna get the final exam. So the final exam covers, exam 1, 2, 3, and then this new material. So exactly how many reactions would I have if I put every single last reaction that we covered this semester on the final exam? We have too many. So what's a likely solution to this dilemma of too many reactions to put on the final exam? What I'll put on the final exam will be the obvious reactions that anybody who's gone through organic chemistry should know. And I won't go over some like esoteric reaction that nobody except who's a specialist in that field knows, more like, the standard old nucleophilic addition using OH or something like that. So it'll be that kind of reactions. I can't because there's not enough space and I have to grade them. So I don't want to make an exam that's so long that I'm sort of looking at the reaction. Oh, they have to know this reaction. They have to know this reaction. And then my exam gets too long and then I can't grade it in time. So it'll be about the same length as a regular exam. So it'll have like, how many reactions do we normally have? Like 10 reactions, 12 reactions. You get to choose to do 10 or something like that. So it'll be like that. It'll be that kind of an exam. But I'm obviously not going to put every reaction on there. So, I could choose out of the reactions that we covered in this chapter and put it on there, but it will not all make its way onto the exam. But you do want to put it on your 3x5 or your 2 pages because, you could get it. And then you might not know the answer and then you might lose points. Okay, so what's going on here? So go ahead and see if you can give me the products. So your textbook actually gives you the intermediate step between the nucleophile that you're adding and the final product. I'm just gonna say for the addition product that, you know, you don't have to actually know what that looks like. So you have to know the final product though. Okay, so what's going on here? Our first reaction is reduction with sodium borohydride or lithium aluminum hydride. What do you get? We've done this in like 3 different chapters. You know what your products is going to be. Let me see if you guys can go ahead and see if you can come up with the answers for this. Because there is, you know, I think there is a value in trying to actually answer the question yourself instead of, you know, letting me do the answer and then just copying off. It's better to copy off than not to write it down at all. But it's better if you can actually try to do the reaction yourself without looking at my answer. See if you guys can do it. Give it a shot. Okay, so sodium borohydride, lithium aluminum hydride, just going to have H minus as the addition. The organometallics, you're basically adding R minus as the nucleophile. The cyanide, you're adding Cn minus as the nucleophile. The Wittig, you just give me the final Wittig product. That's where the oxygen of the carbonyl carbon turns into a carbon and you get an alkene. The imine, you get the primary amine goes to an imine, secondary amine goes to an enamine. The imine is where you replace the carbonyl oxygen with a nitrogen and you have an R group hanging off of it because it's a primary amine. Enamine, you have 2 R groups hanging off the nitrogen replaces the oxygen, and then you have to have a double bond on the carbon next to, on the carbonyl carbon. Okay, so see if you can come up with the product. Okay, yeah, all right, I see. You're either waiting for me to do it or you weren't paying attention and don't know how to do the reaction, one or the other. So anyway, so the first reaction here is just plain old. It's a nucleophilic addition where your addition is with a hydrogen. So that would be what that turns into. What about this? This is where the R is the incoming nucleophile. And I didn't specify what the R is, so you can just say R. So you end up like that. Okay, so then if you add the cyanide, then the cyanide comes in as the incoming nucleophile. So these are all nucleophilic addition reactions. So you know you're going to end up with some sort of an alcohol. So there's the cyanide coming in as a nucleophile. The Wittig, you're just going to take that carbonyl carbon and attach on to it the carbon from your Cr2 group to generate an alkene. So there's the alkene, and that would depend on what you have for the R groups here. Okay, so then for the imine, what do you get? You replace the carbonyl oxygen with a nitrogen. Then you get CH3, CH3, double bond to a nitrogen with an R group hanging off of it. Okay, enamine, what do you get? You get the carbonyl oxygen turns into a nitrogen. It has 2 R groups attached to it. The nitrogen is not charged, it's not positively charged. And then the double bond has to be between the carbonyl carbon and whatever atom happens to be next to the carbonyl carbon. So that's my enamine. So for my acetyl ketyl, if you add 2 moles of the alcohol, what do you get? You get the acetyl. In this case, it's actually a ketyl, but kind of a minor point. Okay, so there you are. All the reactions that we covered so far in this chapter. Yes? Bottom left. Oh, that is, if you add on 1, then you end up with 1 OR and 1 OH. That would be the hemi acetyl. You add on the second one, then you add on 2 ORs, and then you get the acetyl or ketyl. So I could actually, I could ask you for that one. So so right here, I would put in. And I did not put an X there, so yeah, you should know how to do that one. So that's where the OH is still there, and then you have the OR that you just added in. If you add on one more ROH, then you get the two ORs attached to the carbonyl carbon. Okay. All right, so that takes care of all the reactions that we've covered in this chapter. I don't think that we're going to cover anything else in this chapter just because we're running a little bit tight on time. And I would still like to cover a little bit of, if I can, I'd like to get to the electrophilic aromatic substitution reactions, because those reactions are very different from all the other reactions that we've had so far. So I would like to get to that, but if not, All right, so that is the end of this chapter. So this chapter is chock full of reactions. The only mechanism that you're responsible for is just a plain old nucleophilic addition reaction mechanism, and that's all I would hold you responsible for. And not even the complicated nucleophilic addition reaction mechanism. I just say that's simple. The straightforward nucleophilic addition reaction. Okay. So then so we have Friday and Monday. So I'm gonna see if I can get. And the reason why I think it's going to be okay for me to do the next chapter that I would cover is the nucleophilic substitution chapter of carboxylic acid derivatives. And the reason why I think that's okay is we really already covered the nucleophilic substitution reaction mechanism. We went over the majority of the reactions that we're going to cover on this chapter. So we'll just knock off that chapter. I got rid of a lot of slides. We won't even do homework for that. So I think we should be able to pull that off maybe in a single day. And it's the same reactions that we've already covered, same mechanism that we've already covered, just a little bit more nomenclature. But other than that, I think it should be fine. Okay, so I hope you're all so for this class, I said 2 pages, both sides. Okay, so we'll go with that. Because I think in my general chemistry, I think I said still the cards.
Oh, okay.